So last class, I defined this function capital L. And all it was the area under 1 over x. So by looking at this curve, the area from 1 to x, if this is 1 over t, Lx was defined as that area. And that's all we said about L of x. That was the definition, plain and simple. And by looking at that integral and using some properties, FTC1 and FTC2, and some clever U substitutions, we were able to prove that L had all sorts of interesting properties. That L of a product equals a sum, L of a quotient was minus, and L of a power turned into a product. We found a couple points on L. We know that L of 1 has to be 0 because it's the area from 1 to 1, which is 0. And we know that L of E is 1. And the reason we know that is because we defined E to be the number that satisfies L of E as 1. So that's our definition of E. And E happens to be about 2.718. And we graphed L, and it looked sort of basically like this. We know that it's always increasing. We know that it's always concave down. We know that it's defined over the interval, the open interval 0 to infinity. So today, we want to look at another function that I'm just going to arbitrarily call capital E. Just pick a random letter out of the alphabet. And E is going to have the property that it equals the inverse of capital L. Now first, we need to establish whether or not L even has an inverse. Does L of x have an inverse? What does a function need? Now this is going back to algebra 2 and before. What does a function need to be invertible, or what would keep a function from being invertible? Jed? No, denominator 0 has to do with the domain, like whether it's where its domain is, and that's not necessarily related to the inverse.
It's 1 to 1.
Okay, and a function has to be 1 to 1 to be invertible, right? So what does 1 to 1 mean? Means one way you can look at it graphically, it passes the vertical and the horizontal line test. So is L of x 1 to 1? And what does 1 to 1 mean? Does it pass the horizontal and vertical line tests? And what I mean by that, well, I mean if you run any horizontal line across the function or vertical line, does it intersect the function more than once ever? And does L of x seem to be 1 to 1? Yes. Based on what we know? Yeah. L of x certainly seems to be 1 to 1 because any slice I take through it is only going to intersect it once. Okay. But how do I know L of x is precisely 1 to 1? Well, the way that I know that it's 1 to 1 is because I know that L is an increasing function. How do I know it's increasing? Because I proved last class that its derivative is always positive, right? So since L prime is always positive, I'll say yes. Yes, this is true. Why? Since L prime is always positive, then L is always increasing. And an increasing function has to be 1 to 1. Why? Because if it wasn't one-to-one, here's a function that's not one-to-one. That's not one-to-one. It fails the horizontal line test. That function is not always increasing. In fact, specifically, if a function fails the vertical line test, there has to be 2 points where a horizontal line goes through it. And what do we know from Rolle's theorem? If there's 2 points with a horizontal line, what does the derivative have to be somewhere in the middle? 0. So here, f prime would have to equal 0. But L prime is always positive. So this has to be one-to-one. So yes, L has an inverse, which is good because otherwise I wouldn't have anything to talk about for this whole lecture. Okay, so what can we say about inverse functions? So that was a little bit of review, and here's a little bit more review about inverse functions. So here's some properties of inverse functions. If E and L are actually inverses, and I take L of x, and then I take E of x, or I take E of that, what do I get back? Right, I get x back, because E and L cancel each other out. Just like square and square root. And in fact, I could also do it in this order. E of L of x equals L of E of x. So that's one handy property of inverses. Here's another handy property of inverses. If y is E of x for any ordered pair, xy, then x is what? L of y. Because you could just apply L both sides here and get x equals L of y. So if one coordinate is E of x, the other coordinate is L of y. Right? They're inverse functions. What's the other handy property of inverse functions? And this is a little bit more basic, but just from the definition, with an inverse function, everything related to x and y, swap. So if 3 comma 5 is on your original function, 5 comma 3 is on the inverse function. So what about the domain and range? The domain of the original function is the range of the inverse. Exactly. And we know the domain and range of L, so we can talk about the domain and range of E. And in fact, we can sort of sketch out a graph of E. So what can we say about E? Well, the domain of E has to equal the range of L. And look over there at my graph. We saw this last class. L goes all the way down to negative infinity and all the way up to positive. So the domain of E is just negative infinity to infinity. So it's defined everywhere. And the range of E is the domain of L. L is only defined for positive numbers. So its domain is 0 to infinity. And I can even say one other thing, because if we look at L, you see the limit. L goes to negative infinity as x goes down to 0. So I can kind of reverse that. As x goes to negative infinity, what happens to E of x? Yeah, exactly. It goes to, and I can sort of write this out. Well, it's the same thing if I look at what happens as x goes to 0 of L of x, no, I shouldn't say it that way. That's not helpful. I'll just say that. Because as L goes to 0, x goes to negative infinity. So over here, as x goes to negative infinity, E goes to 0. So it just flip-flops. And I can even get a couple points on the graph. I know that L of 1 is 0, so E of 0 has to be. And I know that L of E is 1, so E of 1 has to be E. So those are just the 2 points that I wrote down over there. So if I take all this information and put it together, I can graph E. I know it goes through 0, 1, and I know it goes through 1, E. So we'll say that's up there. I know its range goes to positive infinity. So it keeps going like that. But I know it goes all the way down to 0 here and to negative infinity. And the limit as I go to negative infinity has to be 0. So 0 has to be a horizontal limit. That's the graph of E of x. Now, the other thing you may recall about inverse functions from previous classes is the graph of the inverse is just flipping it around the diagonal y equals x. So if I take this function and flip it around that dotted line, that's L of x. So this, flip it up, turns into E. E is always concave up because L is always concave down. And E is always increasing. L is always increasing. So any questions about the graph of E or its basic properties? Well, okay, so now that I've got this graph, I'm going to guess, I certainly haven't proven this, but to me, E of x sort of looks a whole lot like e to the x power. Certainly not a proof, but it looks like it. So what I'm going to try to do is show that capital E has the same properties of e to the x. And if it does, hopefully eventually I can prove that they really are the same function. And I'm going to do it similar to what we did last class. But last class I had to use the integral definition of capital L to prove all the properties. Well, I don't have to use the integral definition anymore because I know that L has these properties. And I know that E is the inverse of L. So I'm going to prove that E has properties that look really similar to that. And if we think about what properties exponentials have, that can guide our proof here. So one of the properties of exponentials that I'd like to show is this. If I take e to the a times e to the b, then I get e to the a plus b. And that looks a whole lot like this first property. So I know this is true. I want to prove that that kind of property holds for capital E. Okay. So I know this is true, so I want to prove e of a times e of b is e of a plus b. That's my goal. And here's the proof method I'm going to use. And it may look a little weird at first, but then when you see how it works, it's actually kind of clever. So I'm going to start with my left-hand side, prove that it equals the right-hand side. And this is my first step. I'm just going to copy this down again, E of A times E of B. But I'm going to take L of this thing, and then I'm going to take E. Now, why are those two things equal? Exactly, E and L cancel out. So if I take L and then I take E, it's just like nothing ever happened. Okay, so that's why they're the same. But now why did I do that? Because all of a sudden this is more complicated than that. Well, I did it because look here on the inside. This is L of a product. And what can I do with L of a product? Exactly, I can turn it into a sum. So E, that's on the outside, that just comes along for the ride. But on the inside, L of a product is L of the first thing plus L of the second. So I used a property of inverse. Now I'm using a property of L. OK, I'm done. One step. How do I finish this up? How? The E and the L cancel out, right, on the inside. The inside E and L's, that's just A. And that's just B. So this is E of A plus B, which is what I wanted to prove. Huh? It's a box. Box means I'm done. I proved it. Yay. I'm happy. Little box. Yeah. It's like BAM, right? Except it's a box. It's more sophisticated. Questions about the proof? Yeah. OK, so once you've seen this technique, this is actually how we'll prove the other properties of E that I want to prove. So the same trick always kind of works. So we'll use the same template, but we'll just start over. OK, so the other property that I want to prove is if I take E of A divided by E of B, or at least this is, I know this is true for exponents. So I hope this is also true for capital E. So I want to prove E of A divided by E of B is E of A minus B. Can you visualize the proof in your head?
Yeah.
See it?
It's going to be like the same steps as before, right?
Be the same steps as before, but over here I'm going to use this property, which will turn the division into a minus, and I'll be done. All right. So let's go. E of A divided by E of B is E of L of E of A divided by E of B. It's a lot of parentheses. OK, here we go. On the inside, I have L of a quotient, which turns into subtraction. So this is E of L of E of A minus L of E of B. But L of E of A is just A. L of E of B is just B. So it is E of A minus B. So I can draw a box. Questions? All right, so now you try that one. What's the property of exponents that I want to try to prove, and then formulate that for e and then see if you can prove it. And the proof is basically, the same thing. If you figured out what the property is, what are we trying to prove? Exactly. Yeah. So the property is when you raise a power to a power, it just equals that. So how would I write that in terms of e? Well, that just says if I take e of a and raise it to the b power, what would it equal? What would this be in terms of capital E? E of a times b. See? I want to prove if I take e of something and raise it to a power, that's e of the product. Because capital E here is acting like little e to a power. Does that make sense? And you're going to be able to prove it by using this property of L. So see if you can work that, do the inverse thing like we did before, use the property of L. And it should look a lot like that last proof we did. Perfect. Now that I've written it this way, what can I do now? The b can come in front of the L, right? Because of that third property. So it's E of b times L of E of A. But L of E of A is just A. So that's E of B times A. But since multiplication is commutative, it's just AB. Same thing. Ta-da! Box. Happy day. And the interesting thing about this property here, when we proved it last class, L of A to the B, nowhere did I assume B had to be positive or an integer or anything fancy like that. So this works in cases like e of a to the 1/2. That's valid, or e of a to the -3. Because just because L is only defined for positive numbers, I didn't ever use that here because a to the b could still be negative and that still be valid. So, so this property works really for almost all a's and b's. So it's a very powerful property. So if I add those things to the list, I've got all that stuff about E over there, and now I know that E has these properties that look a whole lot like exponents. I want to figure out just a couple other things about E, kind of round off our list. So let's make a list here. I know that E of A plus B is E of A times E of B. That's the first one I proved. And then E of A minus B is E of A divided by E of B. And then E of A times B is E of A to the B power. And all those are properties that are shared by exponential functions. Well, here's the other thing that I want to prove. I want to prove that E of a number actually is e to the k, because that's kind of what we think it is. It certainly has all these properties of exponents. Well, let's do that. E of k is e to the k. Well, I know this. ln of e to the k. That's ln of a power. I can use the third property over there. Oh, you know what? I shouldn't call it ln. I should just call, well, yeah, I'll call it ln, because this is okay. Because last class we defined ln to be capital L. Right? So ln of e to the k is capital L of e to the k. So that's fine. But what is capital L of e to the k? K times, right. But what's L of e? 1. So this is k times 1, which is k. So if L of e to the k is k, then doesn't my property of inverses say that, therefore, because I can just swap these, E of k, if L of e to the k is k, then what does E of k have to equal? Has to equal e to the k. I'm not sure if everybody's following that. Let's do it this way. L of e to the k is k. Everybody's happy with that, right? Let's apply capital E to both sides. K equals, e to the k. Confusing myself. E to the k equals E of k. Because the left side just cancels out. Does that work? So let's add to the list that capital E of something is e to the power. Okay, so now we've done all this work and we've pretty much come full circle. Now, I started with this capital L function that was the area under a curve. I proved a lot of properties about it, but I didn't know what it was. I don't have any function that acts like it. So I just decided to call this thing ln of x. So ln doesn't mean anything to us except now that I've defined it. Well, today I showed that the inverse of L, which is the same thing as the inverse of ln, is e to the x, my capital E function. So that means ln of x and e to the x are inverse functions. And capital E really is e to the x. It has all the properties of an exponential function, and it's actually equal to the E function. So if you think about it, I think this is a really surprising result. Like e to the x, okay, assuming you know what e is, e to the x is a pretty ordinary thing. It's just an exponential function. We can deal with it and we can analyze it. And it just so happens that its inverse is the area under this curve, 1 over x from 1 to whatever. That those things are related is really surprising. But that relationship is going to let us prove our most interesting result from this chapter. I'll do that over here. It'll be very short and kind of surprisingly short. Because all the derivatives that we've used up to this point, I proved for you. I proved the derivative of sine was cosine, and I proved the power rule, and the derivative of cosine is sine, and then all the other trig rules you can get from quotient rule. So now let's worry about these new functions. What's the derivative of ln? Well, that one's easy. I mean, we did that one last class. Because since ln is defined as the area under this curve, then by FTC2, the derivative has to be 1 over x. So we knew that. But now, this one, which is a result that we all know. We all know what the derivative of E is. We talked about it before lunch. But we haven't proven it. Right? So we don't really know it. How would you even go about proving the derivative of e to the x? And why is it, why is it any different from, what's so special about e? What's the derivative of 2 to the x? How would we even go about? Yeah, you know a formula for it. It's not x, it's not that, right? That's the power rule. That only works when it's x to a power, right? It doesn't work when it's an exponent. So the derivative of e to the x is not that. Well, let's see what the derivative of e to the x is. I want to do it this way. Let's let y equal e to the x. I want to find dy dx. Simple enough. Well, if y is e to the x, then I can write the inverse. X is ln of y. Okay, now differentiate this implicitly, or let's take a differential. Dx is, what's the differential of ln y? 1 over y times dy, yeah. Or y prime is another way of saying it. Okay, now let's solve. Y dx is dy. Divide dy over dx is y. Okay, how does that prove anything? Y is e to the x. Boom. The proof is so simple, it's almost not even there.
Why couldn't we just flip the top one since we know it's the inverse?
Where?
Why couldn't we just do like d dx, the thingy, x to the 1, and then t dt? Since we know that's inverse of that.
Inverse is not the same as flipping the,
So you can't just flip it?
it's not the same as reciprocal.
So you can't just flip the t or one.
No, no. But I mean, that's essentially why it works, right? Because in this case, when you take the derivative of the integral, you just get 1 over t. And here I get 1 over y, and if I flip it, I just get y. So that's essentially what's going on. I mean, that's the reason that it works, that the reason that the derivative of this function is itself is because its inverse is 1 over y. So when you take the inverse, it flips, and when you take the derivative, it flips, and then they're the same. Yeah, Will.
So when you take the inverse in this, the second step,
Here?
yeah, could you, I guess you can't write it as x equals e to the y?
X does not equal e to the y. Y equals e to the x. Those aren't.
But do you just flip them, or do you have to do
Well, again, you can kind of see it the same way I did over there. I can take ln of both sides, and that would give me ln of y just equals x because they're inverse functions. But because of that property of inverse functions I wrote earlier, you can swap x and y as long as you turn the function, into the inverse. So f of y will be f inverse of x. So you have to swap both. Other questions about the proof? Okay. So e to the x is this interesting function. It's equal to its own inverse. It's the only function, really, that's equal to its own inverse, except for this infinite polynomial that we found before lunch, but it turns out that that's the same as e to the x. And because it's its own, or not its own inverse, its own derivative, because it's its own derivative, some of the derivative problems we have to solve with e to the x are pretty simple. But it will show up a lot in chapter 6 and whenever we solve differential equations. And you've probably seen, or hopefully seen, e some already in chemistry and physics classes because of this property, a lot of growth rate problems, things where temperatures cool, and if you look at half-life or if you look at the rate of chemical reactions, things like that, they involve e. So what I want to do to finish up, these are the ends of the proofs. We'll just do some examples of derivatives and integrals involving e, and that's what is in tonight's homework. So derivatives are pretty easy. And here's an example. Let's find the derivative of this, e to the sine of x squared plus 1. Well, you would of course be wrong if you wrote that it equaled sine of x squared plus e to the sine of x squared plus 1 and just stopped. Because even though that's the rule, you've forgotten to apply chain rule, right? Right, so e to a power, then we have to multiply by the derivative of that power. So this is going to be times cosine of x squared plus 1 times 2x. So if you write it, this is the chain rule version of the derivative. So the derivative of e to the u is e to the u du. You always have to take the differential of your argument. But if you remember to do that, derivatives with e are pretty straightforward, I think. So those in your book I don't think will challenge you. But the integrals always involve some u substitution. They can be straightforward or tricky. So let's look at an easy one. Let's take the integral of x squared times e to the x cubed plus 2. Now, it may look a little bit yucky, but if you think about how the chain rule works, it's pretty easy to pick out what u has to be. X cubed, yeah, x cubed plus 2. Yeah, because if I let u be the exponent, then du is going to be 3x squared, and everything will work out. So let's just do that. U is x cubed plus 2. So du is 3x squared dx. So this will be an easy one if I just use a 3 and a 1/3. So that turns it into e to the u du, which is, when I integrate it, just e to the u plus c. So that's 1/3 e to the u plus c, which is 1/3 e to the x cubed plus 2 plus c. Okay. So picking out the right u. Okay. We'll do one last one where the u is maybe not so obvious. It might take you a couple tries to figure it out. But once you see it, once you get the right substitution, it's easy. It's one step. Integrate for me e to the x minus e to the negative x over e to the x plus e to the negative x. And don't worry about trying to simplify it or doing any algebra. Just find the right u substitution and you'll be done. answer's on the board. du has to be the numerator. Even if you could set the substitution up the other way, but then you get u over du, which doesn't make any sense. You can't do that. But du over u, the integral of du over u is ln of, remember it's always ln of absolute value of u. But why can I drop the absolute values for this? Yeah, e to a power is always positive. So if you look this in the back of the book, I'm sure they would drop the absolute value bars, but it's not wrong if you keep them. It's not wrong if you keep them. And then plus c. Questions? All right, homework's in blue. We're done. See you next week.